Hi, my name is Adonis Leal, and I will briefly discuss the following paper, a low-cost system for measuring light and electric field waveforms, its calibration and application to remote measurements of currents. For more details, you can read the full paper available in this link that's copied in the description of this video. Well, measurements of light and electric fields are usually performed using capacitive antennas, include flat plate antennas and wipe antennas. If the electric field is varied with time, capacitive current I will flow between the antenna and the ground. Here, this current will be proportional to the dEdt. So, in order to measure the electric field, it's necessary to integrate the signal from the antenna using an integrating capacitor here. So, the electric field E will be proportional to the voltage across the integrated capacitor V out and the integrated capacitance C, and inversely proportional to the effective area of the antenna A and the permissivity of vacuum. This term can be named as calibration factor because we can multiply by the output voltage of the integrated capacitors, then we have the electric field in volts per meter. However, this calibration factor is valid only when we do not have field enhancement factors. This figure illustrates the field enhancement due to the elevation of the antenna here and the presence of any building here. The field enhancement is compensated by introducing the G elevation or the G building in the calibration factor. In this paper, we will obtain the calibration factor for the lighting detection and the waveform storage system by comparing the electric field measured with the LDWSCS with electric field measurements obtained from the instrumentation of the Lighting Observatory in Gainesville. Additionally, we use the electric field signatures of one return stroke that was triggered at CAM blending and was recorded by the LDWSCS. Then we gonna use calibrated electric field of LDWSCS to infer the peak current and compare with the direct measurements of the current at CAM blending. Well, the ground truth field measurement system at log, it's a well-calibrated electric measurement system. And in this work, we use the measurement system that is composed by a flat plate antenna with area of 0.17 square meters. The sensing plate is at height of 1.3 meters. They use a Leal WavePro 7100A oscilloscope to record the electric field waveforms. They also use fiber optic links, and the overall upper frequency response of their system is about 10 megahertz. Now I will speak about the light detection and waveform storage system. So for sensing the electric fields, the LDWSS employs a 0.8 meters long wipe antenna here, followed by a preamplifier. The preamplifier includes an integrator and a unit gain low noise amplifier. The signal from the preamplifier is transmitted via 10 meters long coaxial cable to the main board. So here's the main board, the main unit, that consists of an analog signal conditional circuitry and a digitizing system. The analog conditional circuit includes a 500 kilohertz low-pass anti-aliasing filter here, a 30 Hz high-pass filter here, and a programmable gain amplifier here. The sample rate of the digitized system is up to 1 megahertz. The digitized system has a RTC, real-time clock, which is synchronized with GPS module here. The digitized waveforms and the respective timestamps are sent to a computer-based storage system via serial USB bridge here, and the waveforms are stored in the PC. Here we have some pictures of the LED WSS installed at log between 2016 and 2017. The wipe antenna, preamplifier, coaxial cables, and the main unit board. Calibration of LED WSS. For the calibration of the LED WSS, we measure ratios of the log electric field peak in volts per meter to LED WSS electric field peak in digitized units here. And we measure the peaks for both between strokes and preliminary breakdown pulse. We assume as the calibration factor the arithmetic mean ratio based on data from both return strokes and preliminary breakdown. So we assume the average, the arithmetic mean, so 0.08. It's important to say that this calibration factor is valid only when the LED WSS is installed at log. For any places, new calibration factor must be found here because each building has different enhancement factors for the field. Now, inferring the peak currents from waveforms recorded by the LED WSS. So, as I said before, on August 13 of 2016, the LED WSS operating at log records the electric field waveform for one return stroke in lightning initiated using Hawk and wire technique at the CAN blending located at 45 kilometers from log. So using the calibrated LED WSS electric field record, we computed the return stroke peak current using two empirical field-to-current conversion equations found in the literature. One of them was proposed by Rakov et al. And other by Malik et al. Here we have the peak current record at the channel base. And here we have the electric field record by the LED WSS. So in summary, the LED WSS calibration factor was estimated to be equal to 0.08, with the standard error being less than 1%. And it's important to say that this calibration factor is valid only when the LED WSS is installed at log. For any new installations, one must estimate the new value of gain due to the presence of the building and compute the new calibration factor using the methodology described in this paper. The authors would like to thank whole Bronx of Vaisala for providing NLVN data, and Dr. Human, Dr. Carvalho for providing CAN blended data. Thank you for watching this video and see you in the next presentation.